A vector is an ordered list of numbers. Each number represents a coordinate in some dimension. In ML, every data point is a vector: images, text, users. Two operations define a vector space: addition and scalar multiplication. A norm assigns a non-negative length to every vector. It satisfies four axioms: non-negativity, definiteness, homogeneity, and the triangle inequality. Norms turn vector spaces into metric spaces for measuring distances. In ML, norms are used for KNN distances and L1, L2 regularization. The L2 norm is straight-line distance, Pythagoras in n dimensions, square root of the sum of squared components. This is the default distance metric in most ML algorithms. L2 regularization penalizes large weights smoothly. The L1 norm sums absolute values, like a taxi on city blocks. Unlike L2, it follows perpendicular paths. The key property, L1, creates sparsity. Lasso regression uses L1 to drive some weights to exactly 0. The inner product measures how aligned two vectors are. It equals the product of lengths times the cosine of the angle. Positive means similar direction. 0 means orthogonal. Attention mechanisms compute inner products for similarity. Orthonormal basis. Perpendicular vectors with unit length. Inner product of different basis vectors is 0. Coordinates become simple dot products. This is the foundation of PCA and SVD. A linear transformation preserves addition and scalar multiplication. Every linear transform can be represented as matrix multiplication. Neural network layers are linear transforms followed by activations. Watch how the grid morphs while keeping lines straight. The determinant measures how a matrix scales area or volume. Positive preserves orientation. Negative means it flips. When determinant is 0, the matrix is singular, no inverse. Normalizing flows compute the Jacobian determinant. An eigenvector is a direction that only gets scaled, never rotated. The eigenvalue is the scale factor. A times v equals lambda times v, the eigenvalue equation. In PCA, eigenvectors are the principal components. The chain rule computes derivatives of composed functions. Multiply the derivatives along the chain. This is the foundation of backpropagation. Gradients flow backward, multiplying local gradients. Partial derivatives measure change in one direction, fixing others. Together, all partials form the gradient. We compute partial L, partial W for each weight. This tells us which weights to adjust. Gradient descent follows the negative gradient downhill. Theta becomes theta minus alpha times gradient. Each step moves us closer to the minimum. This is the algorithm for training neural networks. The learning rate alpha controls step size. Too small, painfully slow. Too large, overshooting. Just right, smooth convergence. Learning rate scheduling is crucial for training. The Jacobian is a matrix of all first-order partial derivatives. It generalizes the gradient to vector-valued functions. Each entry ij is partial fi partial xj, used in normalizing flows and sensitivity analysis. The Hessian contains all second-order partial derivatives. It captures the curvature of the loss landscape. Positive definite means local minimum. Newton's method uses the inverse Hessian. Bayes' theorem updates beliefs based on evidence. Posterior equals likelihood times prior over evidence. Start with a prior, observe data, get a posterior. Foundation of Bayesian ML and uncertainty estimation. The expected value is the probability-weighted average. Sum each outcome times its probability. In ML, cost functions are expectations over data. Monte Carlo methods estimate expectations by sampling. Entropy measures uncertainty in a distribution. Certain distributions have zero entropy. Uniform distributions have maximum entropy. Decision trees split on features that maximize information gain. Cross-entropy measures how well Q approximates P. It equals entropy plus KL divergence. Softmax followed by cross-entropy, the classification loss. This is the loss function for training classifiers. KL divergence measures how different Q is from P. Always non-negative. 0 only when P equals Q. But it's asymmetric. D of P given Q is not D of Q given P. Used in VAEs, knowledge distillation, and PPO.